In this video, I am going to show you guys how to solve for the critical angle for a massive object on a hill or a slope. The critical angle is the maximum angle theta can be to maintain a static state. So the question pretty much defines it. What is the maximum angle theta of the slope to maintain a static state? Static state just basically means that the forces are balanced. And so we're going to use this to kind of drive the way our solution for this problem. I'm going to just draw a force diagram. There's a gravitational force of the Earth pulling down on the box. There is the supporting force, always perpendicular to the surface. Cannot be anything but perpendicular for support. And friction is always parallel to the surface. And I'll notate it this way. Always the two surface forces are perpendicular to each other by definition. Alright, since the forces are balanced, because it's at an at-rest condition, when I slide these into tip-to-tail notation, the force diagram will close itself off, which will help us solve this problem. So there's a gravitational force, there's a supporting force, there is a frictional force. The gravitational force, if the mass of the object is m, then the gravitational force is m times g. I'll just label these roughly right now. Alright, what I need to do right here is figure out which angle theta is. I haven't exactly drawn this to scale, so I need to do some work. The technique that I like to use is to draw a xy plane and then draw one that kind of mimics, not exactly to scale, it's just generic, the slope. Now in here there's going to be a wedge that is representative of theta. Theta is to the right, then up at an angle. That's this angle. Now what we can do is we can use complementary angles to solve for the rest of the wedges. So if that's theta, that's 90 minus theta. That's theta, that's 90 minus theta. You could probably do this faster if you remembered your trigonometric alternate interiors and all that kind of stuff, but I haven't. It's been a while. But now I've got basically all of the possible angles, and so now all I need to do is put the right wedge in the right spot. So when I go to my vector diagram, I've got up and to the right and then straight down. And that corresponds with this wedge right here. And so that's not theta, that equals 90 minus theta. And so if I go check the next one, obviously this one's going to equal theta. That's just how triangles work when you've got a right angle. But down and then up and to the right corresponds with this part right there. And that is in fact theta. Alright, now I've got a right angle, whoops, and I've got theta established right here. Now I can represent the supporting force and the friction force in terms of theta. So I'm just going to do this very quick. The support is on the cosine side. So the support is going to equal m times g times the cosine of theta. If you need to see this calculation, please let me know. I'll show it to you. It's just using the opposite over adjacent and opposite over hypotenuse and adjacent over hypotenuse. Alright, there we go. Alright, but I have one more thing that I need to do here to maintain a static state. Here's kind of the trick to the problem. It probably has something to do with how sticky the objects are, so the coefficient of friction. And so, by definition, the coefficient of friction is the relationship of the amount of friction you have for every unit of support. And in the way we've defined support and friction, it works out like this. M times g times the sine of theta divided by m times g times the cosine of theta. Now this is a pretty convenient solution because m times g will cancel out for both of them. And I've got a sine of theta over cosine theta. And I'm going to put an S here because in order to maintain a static state, we're really talking about the static coefficient of friction. Sine of theta over cosine of theta equals a tangent theta. And the question is asking, what is the maximum angle? Well, I'm going to solve for it in terms of theta. It's interesting, it's independent of g and mass. So this relationship works for any object, and it works really in any location, whether it's on Earth or in Mars. It's kind of cool how it works. Anyways, hope this has been helpful. Thank you guys very much.